Welcome to my laboratory. Okay, what's this about then? Well, it's a demonstration of a very interesting electromagnetic dynamical system inspired by the Lee-Tseung lead-out theory. This is a variation of his experiment 001. What we have here is a coil. It's a solenoid on a tube. The coil is, a whole bunch of turns of number 29 magnet wire. And then these are the feeds, power feeds for the wire. This coil is wrapped on a plastic tube. And inside the plastic tube are some little samarium cobalt magnets like this. And actually they have a hole in the middle of them. Okay, so there's two sets of these samarium cobalt magnets in there. You can see the shadow of one set there and the shadow of another set there. And in the end caps of the tubes here and here are a couple of little NDB magnets wedged into those black end caps. And all of the magnets are in repulsion. So these magnets, these poles repel these poles repel these poles repel these poles. So the magnets are all in repulsion. And this coil is just a normally wound coil with several hundred turns of number 29 magnet wire. Okay. And I have the system, as you can see, suspended from a banana hanger. And there's the wires, and there's the feeds. Okay. So it's on there, and as you can see, it's very free to move in the pendulum direction. Okay? Now, I'm just feeding this apparatus directly from the Interstate F34 function generator. And just for grins, I've got the oscilloscope on as well. Now the F34 gives me the ability to sweep as well as put in a DC offset. So I'm going to show you on the oscilloscope what exactly I'm going to do, but since we're going to be doing it at a little bit higher, slower frequencies than is convenient to display on the scope, what I will do first is show you what I'm going to do at a little bit higher frequency. Okay. So I'm going to be displaying a square wave pulse Okay, here we go. I'm going to be putting a square wave pulse into the apparatus, and I'm going to be sweeping the frequency of that square wave pulse from about 1 hertz to about 18 hertz. And then at another point, I'm going to be putting in a DC offset so that square wave pulse will no longer be plus or minus 5 volts. It'll be plus 10 volts to 0 volts. Okay, but for now we're going to use plus or minus 5 volts on that square wave pulse. Okay, so let me set things back to where they were. We're going so slowly that the oscilloscope doesn't do you much good at the frequencies we're dealing with. Okay. Well, let's not worry about that. Okay, now, back to looking at the apparatus. So I'm going to go ahead and hook it up. And I'm going to set the square wave generator to sweep from 1 Hertz to about 17 Hertz, plus or minus 5 volts. Okay. Here we go. Okay, that was 0 to, or rather 1 Hertz to about 18 Hertz, 17 Hertz, with a symmetrical square wave, plus or minus 5 volts. Now, you might have seen some interesting resonances in there, so I'm going to just manually go through and try to find an area where there's something interesting happening. Rocking up and down as the magnets go back and forth. But the center of mass of the system pretty much stays where it is. There's not a lot of back and forth motion, is there? That is pendulum-wise. Well, you might say that's because the pulses are symmetrical. We're pushing the magnet one way and then we're pushing the magnet the other way because we're flipping the voltage on that coil. So let's go ahead and change that. We'll just put in our DC offset. Okay, now we've got a DC offset in there, and as you can see, the magnets are staying over to the left more now. And we're pulsing through that same range of frequencies. So we're pushing the magnets harder in one direction than we are in the other direction. And this should take care of the symmetry. Now we have a very asymmetric situation. But the center of mass of the system still isn't moving. Could it be that for every action there is an equal but opposite reaction? Could it be that momentum is conserved? I encourage you to build this system and experiment with it, and if you find out anything, please let me know.